To learn about Fourier transform, but before that we have to do some integration tricks. And these are some of the integrals that we learned last time. One was we had the integral of e to the negative ax squared dx from 0 to infinity. Actually, was it 0 to infinity or negative infinity? Negative infinity. Negative infinity to infinity was square root of pi over a.
Yes.
And then number 2, we also did the integral from 0 to infinity of sine t e to the negative st dt, which is the Laplace transform of sine t, and that's going to be 1 over 1 plus s squared. Okay, so on top of this, I'm going to add 2 more results integration, and once we are done with those, then I can start explaining Fourier transform. Okay. All right. So first integral I want to do is the integral from negative infinity to infinity of e to the ax squared plus bx dx. Okay, so that's what it is. For this one, we have to use completing the square. So negative ax squared plus b of x. You can first factor out the a. Just like that, okay? And then you can add and subtract the half squared. So half of this is b over 2a, right? So you take b over 2a, you square that, and add and subtract. Just like that. And then the result is that you get negative a, and this much becomes complete squared, something squared. Okay? So that's the point. That's the point of this entire calculation. You know how to do completing a square, right? Okay, it's something squared, right? Yeah. So you learned that in high school. Right? So you do x minus b over 2a squared, and then negative a times this becomes plus a times b squared over 4a squared. That's after canceling the minuses, and I squared both top and bottom, so that you get b squared over 4a. Okay, so with this result, now we can rewrite this integral as the following. This would be equal to negative infinity to infinity of e to the negative a x minus b over 2a squared, and then it could be plus this one, but that can be written as e to the b squared over 4a dx, right? Because addition in the exponent can be split into 2 exponentials. And notice that this one doesn't have any x in there, so I can bring that outside. Whereas this one, this thing here, you can just do another substitution with u equals to x minus b over 2a. Now if this is the case, then what's du equal to? If u is x minus b over 2a, what's du? dx, right? Yeah. Because this is just a constant, so if you apply dd both sides, du is dx. So this can be written as integral from e to the negative a u squared du. And then you also have to think about what goes here and there. So if x is infinity, what's infinity minus some value? Still infinity, right? So the top will still stay as infinity. If x is negative infinity, what happens to u? If x value is negative infinity, what's the value of u? Negative infinity as well. Right? But if you look at this, isn't this exactly the same as this integral? Right? It's just u is changed into x. So we can now say the answer is e to the b squared over 4a times square root of pi over a. Okay. So that's the result that we have to use. 3, integral from negative infinity to infinity of e to the negative ax squared plus bx dx would equal to e to the b squared over 4a square root of pi over a. Now, I'm going to be actually sneaking in some new result that looks like I'm using this one, but I'm really not. So later on in the calculation today, I will be actually doing such a thing, but there will be an I in there. Okay? If there's an I in there, then I'm still going to insist that the answer is this, but there's some precautions that you have to do. You actually have to do something called contour integral on the complex plane, and you have to make sure that that still converges. There's no additional poles giving you some other terms. But we'll just assume that it works as well. Okay? So even if there's an I there, we will still assume that this still works, and it does. Okay? It's just that we don't have enough knowledge about complex integrals to actually explain what happens there. Okay? Now there's actually a more crazy way to do the same calculation, which I don't recommend, but it's still possible. What you do is you can rewrite e to the negative ax squared, and then e to the bx, and then e to the bx is equal to 1 plus 1 over 1 factorial bx plus 1 over 2 factorial bx squared. You remember this Taylor series?
Yes.
Right? This is a Taylor series. So you can replace this by that, and then say that the odd functions, because this one's even, the odd functions will integrate to 0, and these additional ones, x squared, and the other ones you can obtain from here by differentiating by a. So you can actually do this, compute these integrals along with this one. And the nice thing is, if you do it that way, then you can definitely see that this will be true even if there's an I there. But it's quite hard. But the thing is, people doing quantum mechanics or quantum field theory, they end up doing these kind of calculations a lot, so they would do such a thing as an exercise. So it's not like nobody does it. Some people do it. It's just too hard. Okay, and then the next result I need is integral from 0 to infinity of sine x over x dx. Okay. What's the antiderivative of sine x over x? How do you integrate this again? What's the method for integrating this? No, there is no quotient rule for integrals.
Oh, my bad. No.
Yeah. How do you do the integral? Nobody remembers what I said about this integral? Huh? It can't happen. You can't do it. Okay. Yeah. The antiderivative doesn't exist, In fact, if you put this into Wolfram alpha or some other things, it's going to give you some new functions that you've never seen before. Okay, so that's what it is, which immediately makes you question, how are you going to find this value if you don't know what the antiderivative of this is, right? And that's why we use the Feynman trick. Okay, so here's how we do this. Okay, so question. So what we are going to do is define I of s equals to 0 to infinity and make it worse. So I want to put e to the negative sx sine x over x dx. So we want to make it worse. Okay. Now, eventually, what do we want to calculate? I of what? When does this become this? 0, right? If s is 0, e to the 0 is 1, and you just get sine x over x, which is what you want. Okay. So the question is, given this, what is this? That's the question. Okay. All right. But then, notice that if you differentiate this under the integral, and of course there's always this problem of, can you change the derivative with the integral? And there's some other very strict conditions, but we're just ignoring all that, okay? So we're going to suppose it does work. And if that does work, then if you differentiate this as a function of s, then negative x comes out as the chain rule because of the chain rule, right? So that's going to give you negative x e to the negative sx sine x over x dx. X and x cancels, and you get negative of 0 to infinity of e to the negative sx sine x. This is s. Sine x dx. Okay, where did we see this integral before? Number 2. It's number 2, right? Yeah. So what's the result of this?
1 plus s squared.
Yeah, there's a minus in front, but it's 1 over 1 plus s squared. Right? Okay. So that's nice because I know the antiderivative of this. What's the antiderivative of this? Does anyone remember the antiderivative of 1 over 1 plus s squared? No?
Tangent.
Almost. Arctangent. Plus c. Usually you figure out this unknown c by plugging in 0, but we're looking for I of 0, so that's not something that we can do. So instead you have to figure out something else. So instead what I want to say is that I of infinity should be some value. Okay. So first of all, what happens if I plug in infinity into s? What happens to this? What's e to the negative infinity times x? What's that? Here x is positive because it goes between 0 to infinity, right? So what is that? 0. It says 0, right? E to the negative infinity is 0. So I of infinity must equal to 0. Okay. Now, let's think about arctangent of infinity. So remember, here's the tangent graph. That's the tangent graph. And you're restricting the domain from negative pi over 2 to pi over 2 so you can have an inverse, right? There's more graph here, but if you include them, you can't have an inverse because it doesn't pass the horizontal line test. But this one does have an inverse. How do you draw the graph of the inverse? You do this in pre-calculus. You flip over y equals to x. You flip over y equals to x, right? So what you do is you take this thing and you flip over here, and the result is that the vertical lines become horizontal lines, and horizontal lines become vertical lines. Now we do have vertical lines, so guess what this becomes? You have two horizontal asymptotes. Where? Pi over 2. Where else? And because on the right side it gets closer and closer to pi over 2, it's really this side. And the other one we like that. That's the graph of arctangent of x. Okay? So what is arctan of infinity then? What's the arctan of infinity? Pi over 2. Right? Gets closer and closer to pi over 2. So you get 0 equals to I of infinity equals to negative pi over 2 equal plus c. So that c is equal to pi over 2. Okay? Isn't this fun? I kind of like this calculation because you get to figure out things that you thought was impossible. All right, so now what? Because I figured out that I of s is over here, negative arctangent of s plus pi over 2. What's I of 0? If you plug in 0, what's arctan of 0? Is 0, right? Arctan of 0 is 0, as you can see in this graph, right? So it's going to be 0 plus pi over 2. So the answer to this integral is pi over 2. Okay. Now I'm going to write down something slightly different. This one here is an odd function over odd function. If you divide two odd functions, you end up with an even function. Would you agree? Okay. And because this is an even function, if you integrate from negative infinity to positive infinity, it'll be just the double of one side. Okay. So that's what I'm going to write down. I'm going to write down that if you integrate from negative infinity to infinity of sine x over x dx, you get pi. Okay, so I'm going to erase this. Any questions so far? Okay. See how all these basic stuff that you learned in Calc 2 and pre-calculus still becomes relevant? Mm-hmm. Math always builds on foundations, so basic things are important.
What did you do with the 2?
Oh, there was pi over 2, but I integrated from negative infinity to positive infinity. Instead of 0 to infinity, I integrated from negative infinity to infinity so that it's doubled. Because this is an even function. So if you draw the graph, actually, the graph of this is like this. Something like this, okay? Some call this Dirichlet kernel, or some people call this the sinc function, and all that. Okay. So now, let me introduce introduction to Fourier transform. Okay, so this is called the Fourier transform. And the difference is that you might recall that the Laplace transform had a minus there, right? But Fourier transform puts instead I there, okay? Sometimes people use F for the notation. Another nice favorite notation is this hat, which will also be my favorite notation as well. Okay. Now there's also an inverse transform. Let me do it this way. Okay. So inverse transform of f hat s is defined as 1 over 2 pi, negative infinity to infinity, of f hat s e to the negative I s x dx. No, ds. ds. And the result is a function of x, right? Because s is integrated away and you get x. And surprise, surprise, you're going to get fx back, okay? Now, however, again, we're going to rewrite this as upside down, the opposite of this, okay? So the way we are going to think of it, of this transform would be like this one, okay? Okay, now properties. So first one is that it's linear. And if you have Laplace transform of, no, Fourier transform of C1 fx plus C2g of x, it's going to be the Fourier transform of each individual ones. Okay. Now, what's interesting is the following one. If you take the Fourier transform of the derivative f prime of x, well, let's write this down and see what it does. Okay, so if you have the derivative, then that's negative infinity to infinity of f prime of x e to the isx dx. And we can do integration by parts to this one. So what does integration by parts do? Well, the integration by parts is u dv is equal to uv minus v du. So if you think about this one as your dv and this one as u, then if you do the antiderivative, that's going to be f of x, right? Antiderivative of this will be f of x, and you still have uv, so this will still have eisx, and you have to plug in the endpoints, and then minus. Now this time this stays, so v stays, but then you have to differentiate this instead. So you have f of x times is e to the isx dx. And the reason is, as you can see, if you apply the chain rule, the coefficient of x comes down, right? So that's where you get the is, right? And there's some assumption here that f of x is quickly decaying as x goes to infinity, or else the integral wouldn't be defined, right? It would be hard for this to be defined if the function doesn't go to 0. It has to go to 0 so that this gives you a finite value. So with that assumption, what you get is that this should be 0 because you're plugging in x as infinity. So f infinity and f negative infinity are both 0, so that becomes 0. And look at what that is. That really is saying that f prime of x is equal to negative, I can bring out the is outside because that has nothing to do with this dx. So you get fx e to the isx dx. Now look at this. What is this? What is that part? Oh no, it's not number 2. Well, it's like number 2, but I was talking about this one. It's this one, right? Yeah, it's the Fourier transform of s. Okay, so you end up with negative is Fourier transform of S. I really wish you guys remembered the Laplace transform. Oh, I just forgot. So half of you didn't learn Laplace transform at all. Well, Laplace transform has a very similar thing. Laplace transform of the derivative is s times the Laplace transform of the original function. And both of these are used for solving differential equations because it has this nice property of turning derivatives into multiplication by some function. And what it means is that if you have a differential equation, and why do we call it a differential equation? Because it has derivatives there, right? If you do a transform, suddenly all the derivatives go away. What is that? That's an algebraic equation which you can just solve, right? So Laplace transforms and Fourier transforms are used because it has the power to magically change a differential equation into an algebraic equation. Okay? Or if you apply it to PDEs, if you integrate one side, then one of the derivatives go away, and there's still another partial derivative. So the end result is that a partial differential equation reduces to the ordinary differential equation. It's still something because ODEs are a lot easier to solve than PDEs. Okay, all right. So that's the nice property that we enjoy, and that's why we like to use this for PDEs. Okay. Number 3, if you have a, let me see, if you have, so if you have a product of two Laplace transforms, and if you do the inverse product, then you end up with f of x convolution of g of x, where the convolution operator of two functions is the following. It's from negative infinity to infinity of f y minus x g of y dy. Actually, just a minute. It should be x minus y. So x minus y. That's called a convolution. Now, surprisingly, you can do some change of variables and show that this is actually true, equal to negative infinity to infinity of f of y g of x minus y, so that convolutions are actually commutative. So this is the same thing as gx convoluted with f of x. So this convolution is an operator that's commutative. It also satisfies distributive property, and there's also this delta function thingy called, which is like the identity for these kind of functions. So there's some other properties, but we're not going to go that deep. We will, however, need this result at some point. And the fact that this is commutative, I'll leave it to you because do we use it? I don't think we directly use it. It's quite straightforward, but the fact that this indeed is the same, I will have to try to prove it. Yeah. I'll try to prove it. Okay. And that's about it. I guess another thing that we can find out is that if you take these are called Gaussian curves, right? If you take these Gaussian curves and do a Fourier transform, you end up with a Gaussian curve as well. That's something that we're going to see a little later. Okay. So let me try to show you a few things. So first of all, I want to prove 3. Proof of 3. Now, I can to say that the inverse of this is this, the same thing as if I do a Laplace transform of this, you get the product of the two. Sorry, if you take the Fourier transform of the right side, you get the product of 2 Fourier transforms. So let's try to prove that instead. So claim that if you have fx convoluted with g of x Fourier transform, that's same thing as Fourier transform of f of s, Fourier transform of f, and then Fourier transform of g. So let's try to show this. So first of all, you need to write down what that is, and yeah, let's just assume that we do know this. So I'll just use this form. Okay. So I'm going to say f of y, g of x minus y, negative infinity to infinity, dy, and then I'm going to take the Fourier transform of this one, which is to multiply e to the isx dx from negative infinity to infinity. Okay, so that's this one. Are you okay? Looks very confusing, but all I did was I just plugged in this definition and the other definition of this is the Fourier transform, right? I just combined the two. Okay, that's all I did. Okay? So there's no reason to freak out. It's just as it is. I didn't do anything magical. All right. So what I'm going to do is I'm going to switch the integrals around, and that's again a big no-no. So this one goes outside. Well, they look the same, so you might not see what's happening. But what's really happening is that I'm pushing the dy outside. So it's fy gx minus y e to the isx, and dx is done first and dy is done next. Okay, such a way to change things is called Fubini's theorem, and the requirement is that this, as a function of x and y over the entire R2, should be absolutely integrable. So if you take the absolute value of this and you integrate over the entire region, it has to be absolutely integrable. It has to give you a finite value. But again, that's for another class. We're not doing anything that rigorous, so that's what we're doing. But then, notice that fy now is independent of dx, so I can move this outside. And in addition, we can kind of make this thing look like that. So I can make it look like e to the isx as e to the is x minus y plus y. So that's going to be e to the isx minus y, and then e to the isy. How's that? Yes?
Is there a reason why we have to write it like that? Like,
Well, the reason for writing this into that? Okay, well, you'll see. So I replace this by this, then suddenly this part looks like this x minus y. So that's the reason. Okay. So here's what I'm going to do. I'm going to move this fy outside because it's independent of dx. So this is like a constant. So fy goes outside, and the integral goes from negative infinity to infinity, and then you have g of x minus y times e to the isx minus y, and then dx. Again, because this is a constant, I'm going to bring it. I don't have enough room. I'll write it here, but this is what I'm going to do. Okay. All right. So now here you have to think about something. So do you remember when we did this one? we had some like x minus b over 2a, and then I said, well, just set this as u, and because the domain is from negative infinity to positive infinity, nothing really changes. In other words, when you integrate from negative infinity to positive infinity, shifting by b over 2a or any quantity is not going to change the integral value at all. So look at this integral. I can think of this one. Oh, I don't want to use that. X minus y. I can think of x minus y and this x minus y and think of this like u. And because this one also has u. Because dx would be same as du, this can be replaced by du, and this wouldn't change because if x is infinity, u would be infinity. If x is negative infinity, u will be infinity as well, right? So you get my point? So after integration by u, you will see that this thing inside is nothing different from just the Fourier transform of gx e isx dx. This minus y is not going to do anything at all. Do you agree? Okay. So the result of that is that you have negative infinity to infinity fy eisy, and then this thing here, the end result is that y doesn't do anything, and you end up with the function of the Laplace, the Fourier transform of s, or Fourier transform of g. So you have g hat s, okay, and then dy. And then again, this is independent of y, so I can bring this outside, and then look what the remaining part is. What's this? What's this one? It's the same thing, but instead of x, you have y, right? So this is f Fourier transform s, g Fourier transform s. So done. That's the proof. Okay? So that's going to be my item number 5. That if you do the inverse transform of f hat g hat, the same as fx convoluted with g of x. Okay. All right. So the last proof I owe you is the following one. Why does the inverse transform actually work? Okay. So that's the other one I want to show. The inverse transform is proof of inverse transform. Okay. And again, this is not a rigorous proof because there's some additional mathematical analysis theorems that I have to quote, but I'm not too prepared for that. And plus, a lot of you didn't take mathematical analysis, so you wouldn't understand anyways. So here's what I do. So I'm trying to prove that. So we want to show that if you take Fourier transform of f of x and then e to the isx dx, and then if you take this, which is a function of s, so remember this is f hat s, right? And you multiply by e to the negative is, and then instead of x, let's put y so that we can distinguish this x and y, okay? But my goal is to come up with, you end up with a function of y, okay? So if you take the Fourier transform and take the inverse transform, by the way, there's a factor of 1 over 2 pi when you do the inverse transform. Now, depending on the book, some books use 1 over square root of 2 pi for both the Fourier transform and the inverse so that they have the same coefficient. We're just going to go with this other convention. They're both widely used. So this outside integral is the inverse transform, inside is the Fourier transform. So if this is correct, if this is indeed the inverse transform, you're going to end up with f of y. So that's what we want to verify, whether this is indeed true. Okay. All right. And again, we're using the Frobenius theorem, and we're going to switch dx and ds. So dx will go outside, ds will go inside. And here's what we get. We get 1 over 2 pi f of x e to the is x minus y. ds goes first, and dx goes outside. Okay. And then for the inside, I'm going to change that as a limit so that it's something that you can do. Okay? So I'm going to change that as a limit n goes to infinity of 1 over 2 pi of from negative infinity to infinity. I'm going to bring the fx outside because it's independent. And then the integral is from negative n to positive n of e to the is x minus y ds. U as x minus y again, so that this thing would be u plus y, and this would be u, and this would be dx. Okay, and so sorry about that. So this should be u, and this will be u plus y, and then this will be du. Where du is still from negative infinity to infinity, and again, the same kind of logic where you shift, the integral doesn't change because it's from negative infinity to infinity. And then you're going to write this as 1 over limit as n goes to infinity of 1 over 2 pi negative infinity to infinity of f u plus y integral from negative n to n of e to the isu ds du. And now that's a lot easier to integrate, right? So that's going to be limit n going to infinity of 1 over 2 pi of negative infinity to infinity of f of u plus y of e to the isu, and then the antiderivative would be give you iu here, right? It's just like e to the as would be 1 over a e to the as, but instead of a I have iu. Is it good? Are you following me? All right. Hopefully, this isn't too boring. Okay, and then you have n and negative n. Okay, so what are we getting? Well, we still have to integrate by du. F u plus y. Sorry. I integrated by s, so n and negative n goes in here, right? So it's e to the I nu over iu minus e to the negative I nu over iu du. And yeah, so sorry about the long calculation, but there will be a punchline, okay, so just be patient. So what is, according to the Euler identity, what is this minus this? What does that give you? See, the bottom is the same, this same as with Euler identity?
Wouldn't it be 2e?
No, there's a minus there.
Oh.
So Euler identity has cosine plus I sine, right?
Mm-hmm.
This one also cosine plus I sine.
Mm-hmm.
Except the angle is like negative theta here, positive theta there. So you end up having cosine theta plus I sine theta here, and this one will be cosine theta minus I sine theta,
I see.
because sine is odd. So the cosines cancel and you end up with sine. And then if you multiply 2 and divide it by 2, this much right here, guess what that is? Two sine nu divided by u. Okay.
Can you repeat the first step? This is one above it.
So I'm trying to say e to the I theta is cosine theta plus I sine theta. E to the negative I theta is cosine theta minus I sine theta. So if you subtract, the cosines become 0, but you get 2I sine theta here as e to the I theta minus e to the negative I theta. Then if you divide, you get sine of theta equals to e to the I theta minus e to the negative I theta over 2I. Okay. If you recall, this is how we introduce sine hyperbolic. Right? Sine hyperbolic is when you don't have the i's, then it's sine hyperbolic of theta. Okay? The same formula without the I. Okay, so we get this integral, and I guess we can even cancel the 2 and 2. Yeah, we still have to take n to infinity. All right, so where do we go from here? Well, what we are going to do is we're going to differentiate this and integrate this. Okay. All right, so that's what I'm going to do. Okay. So I'm going to do partial integration by parts. U dv equals to uv minus v du. But at this point, I think I'm losing a lot of audience, so let me just quickly do the integration by parts and just see where it leads us. So you end up with negative infinity to positive infinity of f prime u plus y of the integral of sine nu over u. Du. Okay. And the way we are going to do this is right, so there will be a minus sign because of integration by parts requires a minus sign there. And we're just going to, since this is an integral you can't do, sine x over x you can't integrate, right? So we're going to just change this into, say, t. And then you want to say integrate from 0 to u. Then it makes sense, right? Yes.
How come we're doing the standard integration by parts instead of the tabular method.
Oh, yeah, just we can use the tabular, but let's just skip that part, okay? So let's just say, okay, I actually want this to be nu, and oh, you know what? I want this to be negative infinity to this, and then put this as t, and let's see. Is there any part that I'm missing? So here's the thing. If I do nu equals to t, and to change the variables, and dt would be n du, so that you're going to get, this is going to turn into t because originally I just had u, right? But there's this dt, du equals to dt over n, so that this nu will turn into t as well. Okay, so that's where that n went. Okay. Okay, so now we get to use this one right here. Okay. So let's see. Let's look at this one. Yeah. Let's look at this function. I'm going to call this as h of u. Now, as n goes to infinity, what happens to h of a negative value, say negative 1? What would that be? Well, if you plug in negative 1 in here, that's negative n, and you're taking n to infinity, so that's going to be negative infinity and negative infinity. What happens to this interval if they're both negative infinity? What's this interval? This will be 0, right? So if you put anything negative, it's going to be 0 if u is negative. That's what's going to happen. However, if u is positive, what is that?
Pi.
It'll be pi because, well, there's a minus, so it'll be negative pi, right? Because of which one? Here, this one, right? Yeah. So you end up with negative pi if u is positive. Okay. So what happens is that because we're, I forgot the du there. Because we're still integrating by u, when u is negative, this integral doesn't make sense because that just becomes 0. It will just give you 0. So you end up with limit n going to infinity. Oh, so after taking the limit n to infinity, what happens is that you get 1 over pi, integral from 0 to infinity, f prime of u plus y, and then that value is going to be negative pi du. Okay? Alright, so we're almost there. Okay, so we now have pi and pi cancels. Minus can be pulled out, but what's the integral of this? It's the integral of a derivative, so it's itself, right? And you're plugging in infinity as 0. And the assumption about our function f is that when f is evaluated at infinity, it's 0. So it's going to give you 0 when you plug in infinity. Minus of negative f of, when you plug in 0 into u, what do you get? Just y, right? And therefore you get f of y, which is the one to be proved. Okay? Alright. That was much harder than what I imagined. Sorry it took so long. Okay? Alright, so I thought that was going to be very elaborating, but it's not really giving you much, I think. But here's what we got. We got that that the inverse transform does work. Okay, so that's the proof. Okay, now we will actually use this for solving PDEs. Okay. So now let's actually use this for PDEs. Okay. So solving heat equation on the number line, or on the real line. So here's our assumption. We have ut equals to k uxx, the heat equation. Okay. But instead of trying to solve this on a bounded rod, small rod, we're going to assume that x is from negative infinity to infinity. And t is greater than 0, okay? And therefore, there's no boundary condition at endpoints, okay? All we're going to do is we're going to assume that the initial condition, ux0, is some function of x. And that function of x would be some function that decays rapidly at the ends, okay? So that your Fourier transform does exist, okay? So let's just solve this. Let's try to solve this. Okay, so what do? We take the Fourier transform with respect to x, okay? So we're going to take the transform. Okay. And because it's a Fourier transform in terms of x, it just commutes with derivative with respect to t. T doesn't do anything with Fourier transform. Okay. So this is just the Fourier transform of u differentiated by t. Whereas, and because Fourier transform is linear, k can come outside. Now, each derivative of x will change to something. Okay? So the derivatives of x goes away. Do you remember what it turns into? Negative is, right? So it's negative is, and because you differentiate it twice, you square this. And that's u hat. Okay? So that you have ut equals to negative squared is positive, I squared is negative, so you have negative k s squared u hat s. Okay, it's also a function of s, but it's also a function of t. Okay? So what you end up with is a function of s and t.
Question.
Yes?
What happens to the I in the third step?
Oh, well, so the thing I'm using is Fourier transform of f prime of x is negative is of Fourier transform of f. So that's what happens. Okay. That was one of the properties that we went over. And because we differentiate twice, that's what you get. All right. Now you have an ODE. The PDE became ODE. How nice, right? It is one derivative. You can bring this to any student taking the ODE class right now, and they'll be able to solve it for you. Just tell them that this is a constant. It has nothing to do with t, right? So if you think of this as a differential equation for t, and this is a constant, you know that the general solution of this is what? It's e to the negative k s squared t of u hat of 0. That's the general solution, right? Yeah. I mean, it's really just some constant times this, right? Where this is actually it's a constant, but it's really dependent on the value of s. And then if you plug in u hat of s, and then you plug in t equal to 0, you see that this is cs e to the 0th power, so that this cs is really u hat evaluated at 0. Okay? So that's what you get. You get u hat equal to e to the negative ks squared t u hat 0. 0. Actually, I think the confusion is because I'm trying not to write everything, but u hat is a function of s and t, and this is a function of u hat s and 0. Okay? So I guess that's better. You agree? Is that okay? Okay. Just make sure that if you plug in t equals to 0, this becomes e to the 0th power, that becomes 0, and indeed these two sides are right, equal. Right? But then what is us0? This is u hat s0 is really the Fourier transform of ux0, but that's given as f of x, right? Right. So this is what you really need to do. This is well, yeah, this is really negative infinity to infinity of f of x e to the isx dx. That's what it is. Okay. Okay. But now here's what we are going to do. We are going to say that since you have e to the negative ks squared t, I'm going to think of this as Fourier transform of something. Because then I like this, because this is exactly this type. If I can represent this side as a Fourier transform of something, and this is already a Fourier transform, then I know what u is, because to get u I just have to do an inverse transform, and it must be a convolution. Okay? So that's what we're trying to do. And to get that question mark must be the inverse transform. See, the nice thing about Fourier transform is that we do have the inverse transform, so we can use it. Okay. Now, it's a bit confusing because what I have here as x is really s there. But let's try to rewrite that as e to the negative kt s squared minus ix s ds. And we're going to compare this with this result here, where a is kt. Okay. So let's write this down. A will be our kt, and then b would be this much. Okay. Is that good? That must be b, and this is a. Then it matches with this one. Okay. And now we can apply that formula. So it's going to be 1 over 2 pi e to the b squared, so it's minus ix squared over 4a, so 4 times kt, square root pi over a, which is kt. Okay. And this is going to be, well, I squared is negative, so it's going to be e to the negative x squared over 4kt. And this is 4 pi squared, and one of the pi will cancel, and you get 1 over square root of 4 pi kt. That's what you get, okay? All right? And therefore, we have the following. U hat is equal to hat of 1 over 4 pi kt square root e to the negative x squared over 4 kt times f x hat. Right, it's a Fourier transform times Fourier transform. Therefore, if I want to recover u, what do? You take the inverse transform. So do the inverse transform of this, which is the convolution of the two things. Okay. And I said convolutions, you can change stuff. So you can have fx convoluted with this function. Now let's try to see what the actual formula is then. Okay? At the end of the day, you get a rather nice formula. Okay? So the solution, therefore, the answer is uxt is equal to the integral from negative infinity to infinity of f of x, no, f of y times 1 over square root of 4 pi kt e to the negative y x minus y squared over 4 kt dy. Okay, so that's the answer to this question. That's the answer to this question. All right, you might feel like this looks really complicated, but imagine this. This formula will give you the answer right away, regardless of anything you put in here. It's quite a formula. It's just anything you put in here, you just put in here, and then you get the answer. Okay? And because of that, this has a name. This one here has a name. This has the name of heat kernel. And another thing that you might be interested in is what happens when you take the heat kernel. So let's call this as k x minus y, comma t. So that's how we're going to call it. And if I put y as 0, and here's the question. What's the shape of, so what is the graph of kxt? Well, this is just some constant. So it's just fixed t. So fixed t. So t is a constant. Then the shape looks like 1 over some constant e to the negative x squared over some constant. Right? K is some constant, t is some constant. What's the shape of this? Well, this would be, you will have the parent function as e to the negative x squared, right? Don't you agree? Like it's just taking this and just stretching it some way. Okay. What does this look like? What's the highest value of this function? When x is? When x is? 0, right? When x is 0, this gives you the highest value of 1, right? And when x increases, what happens to this function? What's e to the negative infinity?
0.
0. So what happens to this function?
It goes down.
Quickly goes down, right? How about if you go left? Same thing. Square doesn't care about negative signs. It's the same thing. What is this kind of curve called? It's called the bell curve. Okay? It's called the bell curve, or the Gauss curve. Okay? And what happens is that as t goes to 0, this becomes very small, making this as large, right? And this becomes also very large, because t is in the denominator. This overall becomes a very large value. So as t goes to 0, what happens is that it falls steeply, but it becomes like that. So you have like something like this. Okay? And this actually tells you a lot about what's going on when you solve the heat equation. So the intuition that you get from this heat equation is the following. When t is sent to 0, then this becomes so large, centered at x equals to y. So it's right here. That's when peaks. Right? And then, when y is equal to x, so that when you do convolution of the two things, it's only going to pick up the value of fy at just x. So imagine what we know. We know that when t is sent to 0, this integral better give you f of x, because that's your initial condition, right? But why does that work? If you ask that question, is that it becomes so large around y equals to x that it only picks up the value of fy when y is exactly at x. And that's why it just gives you fx. Okay? There's some normalizing factor that, so if you integrate, that's what happens. By the way, if you actually put this into the heat equation, you'll see that this itself satisfies the heat equation. So this is actually a legitimate solution of the heat equation. And if you do integration by parts, so that this differentiates and this gets integrated, and then you can actually show that this is true. So this is what people call a delta function. So that so what's happening is that if you have a function convoluted with a delta function, the result is the function itself. So what I'm trying to say is that this heat kernel, limit of t going to 0 of the k xt, gives you the delta function, so that it recovers the original function. Okay? So you can kind of see another interesting aspect of this. So if you have some initial condition, let's say you have an infinite rod, and you only have the temperature from -1 to 1. So you have some high temperature and 0 everywhere. Now, if you do this computation, at t equal to 0, it will be the same as this initial value, right? The moment t goes to like 0.0001, what happens is that the value here quickly becomes like this. So there's a dispersion. Okay? That's what the heat equation does. So when you have ut equals to some k times the Laplacian of u, what this Laplacian does is that it diffuses the initial condition. Okay? So some lessons. Okay? Oh, why did I erase that one? But anyways, so lessons. Heat equation diffuses. Okay? So in other words, ut equals to Laplacian gives you diffusion. Right? Now, number 2, ut equals to negative k uxx is backwards heat equation. So imagine that time could be reversed. Yeah. Do you see, like in Marvel movies, they reverse the time and then everything goes back, and then at some point you can do it again. If you could do that, there's some problem in the physics, especially for this equation. Because what does it mean to reverse time? You would start from here, and as t goes to 0, what happens? Opposite diffusion means that things clump up, right? And at some points you get delta functions. If you get delta functions, can you go beyond that? Can you go to negative 1? No. The moment you hit delta functions, there's no more solutions. So what it says is that doesn't, or may not have solutions, not always, may not have solutions after some time. So there's a famous equation in finance called Black-Scholes equation. If you are a smart math major, then you can actually apply to go to these quant analysts. So you can make a lot of money by working at the stock market. But the equation that mathematicians try to solve there is called Black-Scholes equation. And that actually it behaves something like this. It's not this equation, it's harder, but it has this behavior. So after some point, you don't know what the result is. So there's a finite amount of forecasts you can do. Okay? Now, there's another thing that you see here, which is that this equation is not physical. Okay, so not physical. Let's put a question mark there, because you see, in physics, there's a upper limit to the speed, right? So if something diffuses, information can only travel with the speed of light. That's the max, right? So there's something strange going on here. The moment you turn this heat equation on, then initial values confined to here will actually give you some non-zero value all the way across, even beyond the speed of light. Okay, so that's like some non-physical thing that's happening. Okay? So you can see that heat equation is in some sense a model, which is not like telling the entire story. Okay? So it's just some kind of model that we take. So that's something that we can get. Okay. All right, and there's this mysterious delta function. What is this delta function thing? Right? So that's something that we will run into a little bit more. Okay. All right. So thank you for bearing with me. I only have like 30 minutes or 35 minutes to do the next topic, which I have to include. So let me go fast, a little bit fast. Okay. So this will be intro to Bessel functions. Now, if you did your homework, then the Laplace differential equation, which is like u r plus 1 over r u r plus 1 over r squared u theta theta equals to 0. This one, when you solve it, at some point you had like u r theta. You were doing separation of variables, and you had this one and theta of theta, and then this one later on you found out that this satisfies like r double prime with r squared plus r times r prime minus sin squared r equals to 0. So do you remember this? Yeah, you had something like this when in your homework, right? So what happens is that if we're trying to do wave equation, 2D wave equation, and actually our goal is to solve this drum problem. So if you have this drum and then you like make sounds of this drum, what kind of sound would it produce? Like it's something related to that one that we're trying to do. Okay. So for that, see the wave equation is. So let's see, 0 equals to Laplacian of u. That's Laplace equation. And then if you do ut equals to k times Laplace of u, that's heat. And then if you do utt equals to k times or c squared times Laplacian of u, that's going to be wave equation. Okay. So that the concavity of u gives you some kind of force on the movement. So that's your wave equation. I already spent some time explaining this. So that would mean that when you try to solve a circular drum, like this one, the equation will become like c squared multiplied here with utt here. And then that would mean that you have ur theta t and t of t. Now we've never done any problem that had 3 parts in a separation of variables question. Okay, so it's rather pretty tough. But what's going to happen is that we only have one lambda before, right? If you do this one, you're going to get lambda 1 and lambda 2. So you're going to get more. Okay, and at some point, what's going to happen is that that additional lambda will turn up, and this one, instead of this one, we're going to have something more complicated, which looks like lambda, actually plus lambda r squared minus n squared r equals to 0. And we can further do a change of variables as x equals the square root of lambda r, so that this becomes a function of x, so it's like x squared r double prime plus x times r prime plus x squared minus n squared r equals to 0. So at some point we have to solve this. Okay? So it's a new type of differential equation that we have to solve. That's where we start running into this thing called Bessel functions. Okay? So what is this Bessel's equation? So Bessel function of the first kind is a solution to x squared, just copying this, but instead of r, let's use y double prime. So y double prime plus x times y prime plus x squared minus n squared y equal to 0. Okay. Which has finite value at 0. Okay. And then there's another one that blows up at 0 that's called Bessel function of second kind. Okay. All right. So that's basically where the Bessel functions come in from. We will actually derive this once we get a better idea of what Bessel function is. But to get a better idea of what this function is, let's just do one. Let's just say n is 2. So and that one is called, usually people use j. I should have looked up why people use j, but j2 of x would be a solution to x squared y double prime plus xy prime plus x squared minus 4 y equal to 0. That's going to be what it is. Okay? some mysterious function is a solution to this differential equation. Of course, when you solve this in the circular drum, n could be 1, 2, 3, 4, 5, even including 0, so you actually have to solve this infinitely many times. Now, before, when we didn't have x squared, it was all easy. We knew that that was called Euler equation, where the solution looks like r to some power, right? Or x to some power. However, the moment you have this, the question becomes 100 times harder. Would you believe that? Yeah, that happens, right? Differential equations are that hard. Like any small minor change in the equation, suddenly the question becomes easy to impossible. Yeah, that's how differential equations are. So if you try to find a solution of this one with some known functions, you'll fail. In fact, there is no functions that we already know that's a solution to this. You can try using sine, cosine, any exponential function, anything that you know to come up with the solution of this, you will fail. Okay? So instead of that, what we're going to do is we're going to say, well, although we don't know what this function is, we know we may want to find this power series. How about that? Right? See, any function has a Taylor series, right? I'm lying. If it's differentiable infinitely many times, then you can have Taylor series. But let's just say that this is something that's differentiable infinitely many times, and we want its Taylor series. We look for a Taylor series. What we do is we solve. So solution as power series. So this is called the power series method. And what you do is you just say y is summation of n from 0 to infinity of an x to the n. That's the power series, right? If you plug in 0, that's a0. If you actually write down the sum, what is it? If you plug in 0, it's a0. And when n is 1, it's a1 x to the first power. And then when n is 2, it's a2 x squared. That's what it is, right? Is that good? You know how to read sigma notation? Okay. So what's the derivative? Well, these are just constants, so all we have to do is just differentiate x to the nth power, right? So n comes down. So nothing has changed. This n comes down. Just do that. Okay. And then if you differentiate again, another n comes down, but this time n minus 1 comes down, right? So an n minus 1 x to the n minus 2. Okay. So we have all the derivatives. Now you plug them in. So here's what we get. We get x squared times... Oh, by the way, there's something important that you should do before plugging them in. You want to rewrite this as x squared y minus 4y. And that's just so that it's easier to manipulate the power series. If you don't, then it's hard to do the manipulation. Okay? So here's what we have. X squared y double prime, which is summation of n from 0 to infinity of n times n minus 1 an x to the n minus 2. Let me just switch places. I'm going to put this in front. Okay? And then plus x times sigma n from 0 to infinity of n times an x to the n minus 1. And then plus, remember we switched this into this, so it's x squared times y, which this is y. So x squared times y. And then minus 4 sigma an x to the n. So that's the differential equation you get. Now, don't be too afraid about this sigma here. This is just a bunch of additions. It's sum of all these things, right? Now, if you have parentheses and sum of a bunch of things and you have something outside, you can bring it inside, right? What's that property called? Distributive property, right? So I can just move this inside, and the result is that you get n equals to 0 to infinity n minus 1 an x to the n minus 2 plus 2. What's that?
It's n minus 1.
No, n minus 2 plus 2 is
Oh,
n, right?
My bad.
Okay, and then sigma, do the same thing here. X times x to the n minus 1, what's that? N, still n, right? And then plus sigma n equals to 0 to infinity, and then this one, an x to the n plus 2 minus, plus, and then let's move that inside as well. Negative 4 an x to the n equals to 0 to infinity equals to 0.
Wait, how did you get the x n plus 2?
There's x squared and the x to the n.
Oh.
I'm distributing. So that this is really, sigma is really gigantic summation, right? And
Right.
something outside can be brought inside, right? So that's what you have, okay? All right, and then the thing that I do not like is this thing, the third term. Why do I not like it? Because that looks different than the other ones. The other ones have x to the n. That one has n plus 2. So we're going to do something called a shifting. So we're going to do shifting. And what you do is you first think about this n equals to 0 to infinity an x of n and plus 2, and then say, well, I wish that n plus 2 was just n. Right? And the way you can do it is by replacing all the n's by n minus 2. Now you should still check that even after doing the shifting, the summation is still the same. So let's do the shifting and then compare, okay? So what is that? If you solve this for n, that's n starting from 2. Just like that, right? Now let's compare this with the original one. What do you get if you plug in n equals to 0? What's the very first term that this produces? When n is 0, what does this become?
0x
A0x squared, okay? And then n increases. Indexes increase by 1 every time, right? So what's the next term? A1 x to the third power, right? And then plus so and so. Look at what this one does. When n is 2, what happens? A of? When n is 2 is where it starts, right? So when is 2, 2 minus 2 is 0, and you get x to the 2. Plus, the next number is 3. 3 minus 2 is 1, x to the third power. And do you see that that's exactly the same thing? Yeah. So this shifting trick just rewrites the series in a different format, still preserving the underlying actual representation. The actual series is not changed, it's just the way you write it is changed, okay? And once you do that, then here's something additional you can do. So let me delete everything. Now, if I do that, now there's another problem. See, this one starts from n equals to 2. I want that to be same as well, but these start from n equals to 0, right? So what we need to do is we have to plug in n equals to 0, 1, and see what it produces, and then take those away. Okay, so let's see, what is this same as? When n is 0, what do you get? 0 times anything is? 0, so 0. The next number is 1, right? When n is 1, what does this become? 0 again. If you plug in 1, it's 0 again. Oh, then after that, n starts from 2, right? So now I can rewrite this as summation n from 2 to infinity of n minus 1 an x to the n. And I love this result because I have x to the n and I have n minus n equals to 2. Perfect, right? So let's do the same thing here. How about here? When n is 0, what does this produce?
0.
0. When n is 1, what does it produce? This time it's not 0. What is it?
It's going to do
1 times
A.
a1
X.
x to the first power. Okay. But after that, now n is 2, right? So 2n afterwards. Perfect. So put summation 2 to infinity of nan x to the n. Okay, let's continue. Oh, this one we already have it in that form. It starts from 2. Perfect. Right? And then, how about this one? When n is 0, what does it produce? Negative 4 a0 x to the 0th power. When n is 1, what does it produce? When n is 1. It will be negative 4 a1 x to the first power, right? And then afterwards it's summation n equals to 2 to infinity nan x to the n. Okay? Now, this is huge, but because we've managed to match all the beginning n and also x to the n, here's what we can do. We can first, I see that this is a constant term, so that's negative 4a0. So this would be negative 4a0. And then there's the a1x and minus 4a1x. If you combine this will be minus 3a1x. And then afterwards, there's a summation, n starting from 2 to infinity. So instead of having a bunch of different summations which made the calculation look really scary, we're just going to have just one single summation so that it's organized well. On top of that, because every one of these have x to the nth power, we can factor the x to the nth power and see what's in there. So let's see, this one, n minus 1, an. The next one is this one, plus nan. And the next one is plus an minus 2. And then the next one is, oh, this is wrong, I think. This should have been negative 4. Sorry about that. Minus 4 an. Good? Do you agree? Okay. And then if you look at what's happened here, it's that this is the x to the 0th term. This is the x to the first term. And this is x to the nth term, and so on and so on. Okay? And that has to equal to 0 as a function. Okay? So for this to equal to a function 0, so if for the left side to produce 0 for any value of x, to agree with the right side, what must happen?
Oh, so like one of them has to be 0.
No, all of them has to be 0. All of them have to be 0. So this must be 0, this must be 0, this must be 0. Now, how would you prove that? Well, it's the same kind of argument that we did in the beginning of the semester when I did the Taylor series review. How do you get the very first term? You plug in 0 both sides, right? Then everything disappears, and this must be equal to the right side, which is 0. Okay? How do you get the next one?
Plug in 1.
No, you don't. Huh? How do you get the next term in the Taylor series? Do you remember? No? Huh? You differentiate both sides, right? So that this goes away and this just becomes negative 3a1 without any x, and then you plug in 0. But because the right side is 0, this has to be 0 as well, right? And then how do you get the next one, like the a2, the ones with 2? What do you do? Another derivative and you plug in 0, right?
Yes.
So what happens? Every one of these must be 0 if you do it, because the right side is 0. If the right side was some other function, then that would give you some of the coefficients, but we have 0 on the right side. So that's what we have, okay? All right, so our conclusion is that negative 4a0 must be 0, and negative 3a1 must be 0. Okay? And it's making us a little nervous because everything seems to be 0. But we want non-trivial solutions. Okay, so you have n squared minus n plus n minus 4 an plus an minus 2 equals to 0. So see what I did? I took this one, and this one. I noticed that all of those have an in there. This is n squared minus n plus n minus 4. That's what I put. Okay? And moreover, this can be canceled. And with this, I can solve for an. So I get that an must equal to negative 1 over n squared minus 4 an minus 2. And this one is true for n 2 or greater, because this is true for 2 or greater, right? Okay. Okay, so this has a name. This one has the name of recurrence relation. Now, some ODE courses include this power series method as well, but since the one here in Stony Brook doesn't have it, this is probably the first time you've seen such a thing. And because we don't have time to do the general power series solutions, for the exam purposes, I will only put this type where this number will be some squared. So this would be like 16 or 9 or some other ones, okay? Yeah. So that it's not too different from this one. And what you have is this recurrence relation. What it means is that if you know the value 2 ahead, 2 before, 2 indices before, then you know the next one. It's just some constant multiple. But look, if a0 is 0, then a2 must be some multiple of a0, right? a2 must be some multiple of a0, so it must be 0. a1 is 0, so a3 must be 0. a4 is 0, so that's 0. a5 is 0. So we just get trivial solutions. What's happening? Are we not? We've done all this work. Are we just doomed to failure? There must be some redeeming thing coming out of this, right? So here's a question. When is this expression invalid?
When n is 2 or
Now, when is this invalid?
Plus minus 2.
Yeah, when n is 2, it's invalid because the denominator becomes 0, right?
yes.
Right. So I actually was lying. When you have a2 equals to something times a0, this is undefined, so it really doesn't tell you anything. So what happens is that the other cases are right. So this forces a3 to be 0, a5 to be 0. All the odd ones will be 0 because this is never 0 for the odd ones. When n is odd, this is never 0. So if a1 is 0, that forces a3 to be 0, a5 to be 0. All the odd ones will be 0. Okay? On the other hand, a2 can be a2. Okay. You can just let a2 be a2. Right? There's no condition for a2. a2 can be anything. But once you get the value of a2, that forces a4 to be some multiple of a2, and a6 will be some multiple of a2, and so on and so on. Okay? So let's see what that means. Okay? So we're just going to use the recurrence relation over and over again. So when n is 4, we have a4 equals to negative 1 over 16 minus 4a2, which is negative 1 over 12a2. when n is 6, a6 is equal to negative 1 over 36 minus 4, a4. But a4 is negative 1 over 12. So it's negative 1 over 32 times negative 1 over 12, a2. So that's going to be, I give up. What is this? Help me out here. It's 432? Is it right? I'm just guessing. Come on. 64, 32, 384, okay. It's 1 over 384, a2. And let's just do one more, okay? N equals to 8, that's a8 would be negative 1 over 64 minus 4, a6, which is negative 1 over 60 times 384. And frankly, you can just leave it like this. You don't have, I don't want you to really be using a calculator. Just leave it like that, okay? So, we can continue this, and what's the result? We see that the solution of that equation is y equals to, everything is factorizable as a2, and there's the a2 times 1, x squared, because a2 is the coefficient of x squared, right? That was our original deal. So an is the coefficient of n, right? So a2 is the x squared coefficient, but then there will be minus 1 over 12, which is x to the 4th, and then minus 1 over 32, which is, no, it's plus 1 over 384, x to the 6th, and whatever that is, 1 over 60 times 384, x to the 8th, and so on and so on. Okay? So that's the solution to this. Okay? Now what's amazing is that we will be able to find the pattern in general, okay, and write that as a compact solution. And you can even rewrite that as an integral of something. So from this power series solution, you can find the general form, and from there you can also find the integral form. So you end up with like many different names for this function, and this function will of course satisfy many interesting identities, and we'll learn about them. But right now, the first step into accessing such a function is through this power series. Okay. Now one more comment. This is what's called a singular differential equation, because when x is 0, briefly y double prime disappears, right? You end up with y prime, a first order differential equation. When there's a jump in the degree of the differential equation like that, you call that singular differential equation. And singularities are bad. Often, if you have singularities, there's no guarantee of solutions. But however, this is what's called a regular singularity. So it's among the, there's the irregular singularity, which is the really bad one. In such a case, you might not be able to find a solution. But if it's the regular singularity, which this is, then you can find two solutions. And what could happen is that one solution may look like a power series, but the other solution may look like something multiplied to this. So there will be a second solution that looks like this. Or another worst case is sometimes you might have an ln of x attached to it as well. So for the second solution, okay? In fact, what happens is that for these integers, we call this the alpha, alpha squared. For those integers, this does have a logarithmic singularity. There's another solution that has logarithmic singularity, which makes it really hard. But if it's not an integer, then the other solution looks like there's some 1 over x, or some 1 over some, could be some fraction as well. You know, something like this could be in front of that to make this not a differentiable function as 0. But nonetheless, it will be still, you can write in this form and still be able to find the other solution, okay? So that's what's going to happen. But this other one, that's called Bessel function of the second kind, is for the moment, it won't be our concern because these are not physical, because if you have a pole, like 1 over x, that's not physical because it blows up as 0, right? Same thing as the our polar Laplace equation, that wasn't physical. So, or even the ones with logarithmic, it's not physical. Log of 0 is negative infinity, so that's not physical either. So because of that, the one that we will be working with will be the one, at least for the integer case, the ones that have the power series. Okay. There is also another case when that's when we do some other types. Sometimes both of them look like x3r. So this method is called the Frobenius method. So this finding the solution in this general form is called the Frobenius method. And the Frobenius method, I don't know, if we have time, we might do an example like that. This might have an odd power for some other kind of differential equations, okay? Yeah, but for now, we'll be content with this one, and this will be part of the exam 2 as well. Okay? All right, that's all for today.